Okay, welcome back everyone. So in today's video I'm going to be talking about quadratic residues in number theory. And in this video you'll especially see why I discussed primitive roots in the previous number theory video. That's because, well, they're very important in understanding what numbers actually are quadratic residues. So as you might notice, we have this familiar circular diagram, which I will discuss in 1 second. First, what is a quadratic residue? Or what are quadratic residues? Well, let me write this quickly. So we're going to deal mod primes because although quadratic residues are not restricted to primes, when we deal mod primes, we have some nicer properties for quadratic residues, which I will show you one major property that primes have that composite modulos do not have. So that is why we're going to deal with primes for the most part. So I'll just note that P is a prime. So notice that A is a residue mod P. And since it's congruent to, since this perfect square, when reduced mod P, outputs A as a residue, we call A a quadratic residue. And in fact, all quadratic residues mod P satisfy this equation, right? So for example, and this is showing you that P does not necessarily have to be a prime when we're dealing with quadratic residues. If we consider x squared is congruent to A mod 4, purely 4 is not a prime number, so this is an example, then, well, A, we know that, and it's easy to show that A can only equal 0 and 1. So 0 and 1 are all quadratic residues mod 4. And I'm using the equal sign here because A is a residue here. So, yeah. Okay. Well, let's see. Oh, and I should probably note that although I said A can equal 0, normally we consider 0 as a quadratic residue, as not being a quadratic residue, and but also not being considered a quadratic non-residue. And a quadratic non-residue is pretty much the opposite of a quadratic residue. It's all values A such that perfect squares cannot reduce to A mod P. Okay? So again, A does not fall into any of those categories. It's a separate category. It's on its own. Okay, so now let's see what values can be quadratic residues, and this is where our primitive roots come into play. So let's look at this circle diagram. Now this is the example that we worked with regarding the primitive roots video that I recorded a few days ago. And again, 3 is a primitive root mod 7, and here we're showing that, well, all of the powers of the primitive root 3 result in all of the residues. As we know, that's a property of primitive roots. That is very useful. Okay, and well, I want you to look at all of the even powers here. So 3 to the 0, 3 squared, 3 to the 4, all of these, so I'm going to underline these. And notice that, well, in general, I'll note this as 3 to the 2k, where k is some natural number, where k is some non-negative integer. So, and notice that, well, this is going to be, well, I guess I can just say equals. This is equal to 3 to the k all squared. And therefore, this fits the definition of quadratic residue. Because if we reduce this mod P, we'll get some, I'll just say quadratic residue mod P by this definition. Therefore, all of the even powers of our primitive root are clearly going to be quadratic residues. Okay, well, how about the odd powers? Can odd powers be quadratic residues when reduced mod P? Well, let's see. So I want to prove to you actually that these odd powers are never quadratic residues. Okay, so let's see. How do we prove that? So I'm going to let k equal 2n plus 1. Okay? And we're going to consider the following. We're going to consider x squared is congruent to g to the k mod p. Okay, so by way of contradiction, we're assuming that k is in fact a quadratic residue, which would satisfy the following, which would satisfy this. Okay, so we want to arrive at some kind of contradiction. So I'll just write by way of contradiction here. Suppose. Okay, so, well, I'm going to now write x as a power, as some power of our primitive root, and this is where our fact that the powers of g generate all residues mod p, and therefore non-zero residues mod p, so x is non-zero. And that kind of tells us why 0 is separated, right? So we're going to replace x with some g, so I'm going to say x is congruent to g to some, I'm going to say m. Okay? Mod p. So plugging that in, we're going to have g to the 2m is congruent to g to the k mod p. And notice that while the powers of the primitive root cycle after every p minus 1 power, and therefore and also that tells us that obviously the all the powers less than that are going to be all distinct, and they're going to represent all the residues mod p, as I've stated multiple times, non-zero residues mod p. So therefore, by Euler's theorem, we need the exponents to be congruent mod phi of p, which is p minus 1. Okay? Well, what does this tell us? If we plug in k as 2n plus 1 and subtract both sides by 2n, we're going to get 2m minus n is congruent to 1 mod p minus 1. But since we're assuming p is an odd prime, and, well, that tells us that p minus 1 is even, and that tells us that, well, notice that the left-hand side is even, but I'll just write this out to be as an equivalence so that we're more comfortable in our domain of equal signs. So we're going to have some even number, p minus 1 times, I'll just say b, or q is good, p minus 1 times q, so this is, all that matters is this is some even number, plus 1. So that tells us that an even number plus 1, well, that's an odd number. That tells us that an even number is equal to an odd number, which is a contradiction. Therefore, we have arrived at our desired contradiction. Okay, so what's next? Well, now I want to quickly tell you the fact that I mentioned earlier, which is why we're dealing with mod primes. And I'll give you that fact right now. Well, I'll just actually articulate it because it's not too hard to articulate. And that tells us that, well, all the solutions for x to x squared is congruent to a mod p. There are only two possible, there are no more than two possible solutions for x is congruent for every quadratic residue a mod p. And so to prove that, well, if we have x squared is congruent to g to the 2k mod p, since a is a quadratic residue, it's going to be g to the primitive root to some even power. And if we subtract g to the 2k on both sides, we have, and use difference of squares, we have g plus g to the k, and x minus g to the k is congruent to 0 mod p. And this is where the difference comes in. If p, so since p is prime, we have this nice fact that p divides x plus g to the k, and or p divides x minus g to the k. And that tells us that x is congruent to negative g to the k, or so the solutions are x is congruent to negative g to the k, or I'll just say, to be concise, solutions x is congruent to plus or minus g to the k mod p. But if p was not prime, we don't have that nice property that we can work with, right? We would have to further we would have to further factor these into its prime factorization, and it's much more complex for composite primes. And in fact, a counterexample to this, in case you're interested, where p is composite, is 1 mod 8. So I'll let you see that, well, if we set this congruent to x squared mod 8, it is in fact a quadratic residue, then there are more than 2 solutions to this. Okay. Well, let's continue. So now we're going to get to the last major idea that we're going to learn about today, which is just very simple, using the tools that we've learned here. So I want you to consider x and y are quadratic residues, and a and b are quadratic non-residues. So I want us to figure out what x and y, so whether x and y is a quadratic residue or quadratic non-residue, whether xa, and this is analogous, it could be ya, it could be xb, it could be yb, is a quadratic non-residue or quadratic residue, and whether ab is a quadratic residue or quadratic non-residue. So let's just analyze these. So notice that since these are quadratic residues, we can write x and y as some even powers of g. So g to the 2, let's say n. I'll actually just use x1, just so that we have enough variables to work with, mod p, and then y is congruent to g to the 2y1 mod p. So now what happens when we multiply these guys? Well, we just add the powers, g to the 2 times x1 plus y1 close parentheses. Or in other words, xy is, I'll just write it out, g to the 2 x1 plus y1. But since this is an even power, this is still a quadratic residue. Therefore, xy, if we multiply 2 quadratic residues, we get another quadratic residue. Okay, well, now let's look at this one, x times a. I'm going to go a bit quicker with this one, and you can kind of fill in the gaps of it by writing it down like I did with this first example. But since a is a quadratic non-residue, then a is going to be, then the power, I'll just articulate it, then the power of a is going to be odd. And the power of x, well, it's even. So if we add the 2 powers, well, we're still going to get an odd number. An odd number plus an even number is an odd number. Therefore, the resulting power is odd. And therefore, due to the fact that we proved here, it's a quadratic non-residue. So this is a quadratic non-residue. This is a quadratic residue. And this, well, let's see. It's an odd number plus an odd number, which is an even number. And therefore, its G2 is an even number, which is a quadratic residue. So it looks like the quadratic residues have beaten the quadratic non-residues in this match. Okay? Well, now I'm going to introduce you to a string symbol, which, yeah, you'll know when I see it. You'll know how strange it is when you see it. So I'm going to introduce the Legendre symbol. So this is the Legendre. It's called the Legendre symbol. So, and I'll define it quickly. So the Legendre symbol of A with P. Also, I don't actually know if I'm pronouncing it correctly, but hopefully I am. Well, the legendary symbol of A, mod P, I guess, I don't know if it's A with P, A mod P. I guess I'm just going to say the legendary symbol of A and assume that P is already there. Then it's going to output a 1 if A is 1, if A is a quadratic residue. It's going to output a -1 if A is a quadratic non-residue. And it's going to output a 0 if A is congruent to 0 mod P. So the 0 case is separate, as we've seen throughout the video. Okay, well, let's see. So this is not some mathematical secret. It's purely for as notation. So it's just like helpful. It's kind of it's mathematical convention, you can say. Okay, well, one nice property of the legendary symbol, and it pretty much follows from what we worked out here. So the multiplication of quadratic residues and quadratic non-residues. It follows that the legendary symbol of A also is multiplicative. So that tells us that a legendary symbol of A times the legendary symbol of B is equal to the legendary symbol of A times B. Now, I like analytic proofs of these kind of things, and it might be a bit overkill, because this is kind of obvious from what we've done here. But in the next video, where I'm going to actually talk about the Euler's criterion, which will further be used for the next number theory video, we can easily prove that this is the case. So I'll probably prove this in that video. But for now, let's just take this for granted. Okay? Well, that is pretty much it for what we need to know about quadratic residues right now. And actually, I have a very nice problem which will kind of sum up what we have learned here. And in general, it's also just a nice number theory problem. So I'll just clear the board, and I'll see you then. Goodbye. Okay, so we're back. So here's the problem. So let P be a prime. Prove that there exists an integer A such that P divides A squared minus A plus 3. If and only if there exists an integer B such that P divides B squared minus B plus 25. So let's begin. Well, we have some ugly polynomial here, so and also we're dealing with quadratic residues, so why don't we complete the square for both of these? So let's do that. You might think that we'll end up with some nasty fractions, but you'll see how we mend that quickly. Okay, well, if we have A squared minus A plus 3, then, well, we have to add and subtract 1/4. It's going to be minus 1/2 all squared, which is 1/4. So what we get is, well, A squared minus A plus 1/4 minus 1/4 plus 3, which is nothing but, well, now we'll have the square here, obviously. So we're going to have A, and then minus, well, this coefficient over 2, which is minus 1/2 all squared, and then 3 minus 1/4, well, that's just 11/4. Okay? Well, again, here are the nasty fractions. So wouldn't it be nice if we could just scale this by 4 and we would get rid of all of the fractions, since, well, we're dealing with an integer problem. So in other words, what we want to show is that if we call this expression z, if we want to show that if P divides z if and only if P divides 4z, such that this would not harm the problem by multiplying by 4. Well, let's see. So notice that this way is trivial. That's going to be true, but the other way is what we want to be clear with. So the other way is going to be true, is always going to, so let's just make this clear. So this way, if P divides 4z, that implies that P divides z. Well, this is always going to be true since p is prime, but unless p is 2, because then, well, p is 2 is a prime, and 2 divides 4, so that will not necessarily guarantee that p divides z. Okay, so let's look at the p equals 2 case. So when p equals 2, well, let's reduce this expression mod 2. So by Fermat's little theorem, a squared is congruent to a mod 2. So we're going to get a minus a plus 3 has to be congruent to 0 mod p, since p divides the expression. And p is 2, obviously, in this case. So these cancel, and this goes to 1. But 1 is not congruent to 0 mod 2. So this is a contradiction. Therefore, p cannot equal 2, so we're safe. Okay, so now we have a much nicer expression to work with. So now we have the expression p divides, well, we're going to have, if we multiply that by 2, we're going to have 2a minus 1 all squared plus 11. So now we can do a similar thing with this expression. With that expression, well, let's try to do some things in our head, or I'll just work it out here. So again, we're going to have to add and subtract negative 1/4. So we're going to have a squared minus a plus 1/4 plus 3 minus 1/4. And this is, let's see. Well, you can pretty easily work that out. Oh, sorry, we're over here. Yeah, I got a bit confused there for a second. Okay, so our 3 should be a 25, and that's not going to be a. So I should probably just erase this whole thing. So we're going to have, well, b squared minus b. And then, obviously, plus 1/4. But then we're going to have plus 25 minus 1/4. Okay, and if we multiply the top and bottom by 4, this becomes 99 over 4. And this becomes this perfect square, which is similar to this, but with a b. So 2b minus 1 squared. Not 2b. It's going to be just b minus 1/2 squared. Okay, and plus 99 over 4. And again, by a similar argument, or the same argument pretty much, we're just going to have that we can multiply this by 4, and that won't impact anything. Okay, so if we multiply that by 4, we're going to get the expression, which I'll write down here. P divides 2b minus 1 squared plus 99. Okay, so now I'm going to reduce these mod p. So the first one tells us that 2a minus 1 squared is congruent to negative 11 mod p. And the second one tells us that 2b minus 1 squared is congruent to negative 99 mod p. So this is the case. Either when negative 11 is congruent to 0 mod p, or negative 11 is a quadratic residue mod p, since it's equal to square. So, and the same applies to this. So that tells us that our problem has reduced to proving that so negative 11 is 0, or yeah, I guess another way of doing this is Legendre, I misspelled that brutally. Legendre of 11 is 0 or 1 mod p, if and only if Legend, I'll just abbreviate it with leg, of 9 minus 99 is 0 or 1. And to explain that, well, that's just another way of rewording what I just said. Either negative 11 is congruent to 0 mod p, which is just, by definition, the Legendre symbol tells us that if it's congruent to 0, then Legendre of that outputs 0, and if it's a quadratic residue, outputs a 1. Okay, so this is what the problem has amounted to. Okay, so how do we go about proving this? Well, wouldn't it be nice, this would directly follow if we had that -11, the Legendre of -11, is equal to the Legendre of -90, 99p. So is this true? And the reason being is that if this was true, well, everything that is listed here would directly follow here, right? Since this is dealing with -11, this is dealing with -99. And 0 and 1 are two Legendre symbols. Okay, well, how do we go about this? So notice that by the fact that it's multiplicative, which I talked about earlier, we can split this up as 9p times the Legendre of 11, of -11. Okay, but notice that assuming that p is not 3 for a second, we'll deal with that case later, then we know that 9 is a quadratic residue mod p, since it's 3 squared, mod p not equal to 3. Okay, and furthermore, well, so that tells us that this is going to be 1 if p is not 3, and that satisfies this congruence. But we also have to be careful, because if p is, we also have to have that p is not 11, just to be careful here. But if we analyze these cases separately, we notice that if p is 11, this actually still holds, because notice that, well, 11 divides 11, -11, so it's going to be 0 mod 11, and -99 is divisible by 11, so it's also 0, and therefore, well, this follows, right? This is true here. But now let's look at this case, which is a bit stranger. So if p is equal to 3, then, well, if we reduce these here, -11 is going to be 1 mod 3. Okay, and, well, -99 mod 3 is 0. So notice that, well, this tells us, this holds, because this tells us that, well, 1, which is a quadratic residue, so in this case, if p is 3, then we have that the Legendre will output a 1, and that implies that Legendre of 99, which is 9 times 11, and 9 is a quadratic residue if p is not 3, which is 1, if p is 3, then that won't hold, right? So if p is not 3, then it'll be 0, which holds. So that direction is correct, right? But if we look in the other direction, where -99, we have -99 here. Notice that that is congruent to 0. Notice that that is congruent to 0 mod 3. But that actually implies that -11 is going to be be congruent to 1, or it's going to be the Legendre of -11 is 1. So that actually finishes all of our extra cases, and thus it finishes the problem. So I hope you enjoyed that video, and again, comment down if you have any suggestions for future videos, and have a nice day. Goodbye.